Hello everyone, welcome to Mathematic 1. Today me and my partner Ung will show you how to find min and max value of a function. So here's the roller coaster, and I know that there would be a lot of up and down along the ride. And just by observing you can point out the highest or lowest point, but in reality, how exactly can you calculate the height of this point? Okay, let's take Messi as an example for a second. He's practicing kicking the ball into the air, and we graph the height of a ball as a function of time. So I noticed that the maximum height of the ball is where it stops going up and starts going down, which is this point. I also see the maximum value is right between where the derivative is positive and the derivative is negative, or when the slope changes from going up to going down. The logic is the same for minimum value, which is the point between the derivative is negative and the derivative is positive, or when the slope changes from going down to going up. So from the graph here we have maximum height, maximum y, and minimum height, minimum y. But what about the other 2 points? We will then discuss about global maximum minimum and local maximum minimum. Global max is at some x value like x max, where fx at that point is greater than any other value in the region. Global min is at the x value, let's say x minimum, where the value at that point is less than every other point in your region. And the example is global max is Mountain Everest and global min is the Dead Sea. For the local max is just a locally highest point where fx is greater than fx for any point around it, like the Phan Xipang mountain in Vietnam. And local minimum is the same way, it's the minimum value in some nearby area.
There are 3 steps to find out the maximum and minimum points on the graph and whether they are global or local maximum or minimum point. Let function y by fx equivalent. The first step is find the derivative of function fx. The second step is the function has a minimum value at x is equal to a if the derivative of the function at the point is equal to 0 and the second derivative of the function at the point is negative, where the function had the minimum value at x is equal to a if the derivative of function at the point is equal to 0 and the second derivative of the function is at the positive. The final step is compare maximum or minimum value together, and then which one had higher or lower value are the global maximum or minimum point, and the rest are local maximum or minimum points.
So here you can use min-max to find the number of hours you should sleep to maximize your test score, or the number of tables in a coffee shop to minimize the total cost.
Let's move on to practical application. The question is the rancher can afford 300 feet of fencing to build a corral that is divided into 2 equal rectangles. What dimension will maximize the corral areas? From the picture, we can have the formulation of the corral area A equal to 2xy and the perimeter is 300 equal to 4x plus 3y. So the perimeter equation for y then plug the result of y into the corral area equation. As the result, we get ax is equal to 200x minus ax squared over 3. Now we will determine the domain of the function. You can have negative length of fence, so x can be negative and the height x can be 300 divided by 4 or 75, so this one is the domain of function. Then we need to find the critical number of ax in the open interval from 0 to 75 by setting its derivative equal to 0 to so, and we get x is equal to 37.5 and the second derivative of a is equal to minus 16 over 3, which is smaller than 0, so 37.5 is the maximum value of function ax. Now we will evaluate the function at the critical number and at the end point of the interval. From the calculation, we can say that the rancher could build a corral with the area of 3,750 when x is equal to 37.5.
Okay, thank you for listening to our presentation.
Created using Powtoon.